There are storms that sweep across seas, tearing at ships and shorelines. There are storms that climb the atmosphere, towering clouds heavy with thunder. But beyond the earth, in the silent theater of the cosmos, there is a storm unlike any other. Does not howl with wind, it does not rage with rain. It bends the very fabric of space and time, pulling the heavens inward. Here, light itself is caught, trapped, and devoured. Stars vanish, galaxies tremble, and entire regions of the sky dissolve into darkness. Astronomers call them black holes, yet even that name cannot capture their enormity. They are storms without surface, tempests without sound, a paradox, invisible, yet more powerful than anything known, silent, yet roaring across eternity. What falls within them is not merely matter, but history, memory, the very information of reality itself. The image is terrifying, a storm so complete that even the sky cannot escape, and yet it is real. Black holes are not distant myths, not rare curiosities. They are everywhere, haunting the centers of galaxies, shaping the stars around them, perhaps even steering the destiny of the cosmos itself. What are these storms that eat the sky? Are they the final graves of suns, or are they beginnings disguised as endings, gateways to hidden truths, or even to other universes? This is their story, not only a scientific inquiry, but a meditation on destruction, impermanence, and the fragile laws that hold the universe together. The storm is real. The storm is eternal, and one day it may come for everything. The story of the storm begins long before it had a name. For millennia, humanity looked to the night sky and saw permanence. Stars wheeled across the heavens with patient regularity. Constellations repeated their paths as if carved into eternity. The universe seemed steady, fixed, immune to collapse. Yet hidden in those points of light were subtle irregularities. Stars that flickered without rhythm. Companions whose orbits betrayed the pull of something unseen. A shadow was moving in the sky. Long before astronomers had the words to describe it. The first speculations in the late 18th century, two men dared to imagine the impossible. In England, the natural philosopher John Mitchell asked what would happen if a star was so massive, so dense, that its gravity prevented even light from escaping. Almost simultaneously, in France, Pierre-Simon Laplace wondered the same. They called them dark stars. The concept was extraordinary, a seed planted in the soil of Newton's gravity. At the time, light was thought of as particles, subject to attraction like stones thrown into the air. If gravity could bend a planet's path, why not a beam of light? If the escape velocity of a star exceeded the speed of light, then even brilliance itself would be imprisoned. These ideas were elegant, but they had no evidence. They were curiosities, filed away in the margins of natural philosophy. For more than a century, dark stars remained only speculation, too strange to be tested, too radical to be believed. Einstein's revolution, the storm, gained new meaning in 1915, when Albert Einstein unveiled his general theory of relativity. Gravity was no longer a force pulling across space. Gravity was the shape of space itself. Matter told spacetime how to curve, and curved spacetime told matter how to move. Einstein's equations carried within them a frightening possibility. Spacetime could fold in upon itself so completely that escape was impossible. Black stars, the old speculation of Mitchell and Laplace, were reborn not as curiosities, but as solutions to Einstein's theory. That same year, in the trenches of the First World War, Karl Schwarzschild, a German physicist and soldier, solved Einstein's equations for a simple case, a single, spherically symmetric mass. His solution revealed a critical radius, a point of no return. If an object collapsed within that radius, nothing, not even light, could escape. The event horizon had been discovered, and with it, the mathematical skeleton of the storm was revealed. Einstein himself was unsettled. He doubted nature would allow such extremes to form. He considered them mathematical artifacts, not physical realities. Yet the equations did not waver. The storm was there, lurking in the fabric of relativity, waiting to be found. The first signs in the sky, the middle decades of the 20th century, brought new eyes to the cosmos. Radio telescopes began detecting signals the human eye had never seen. Among them were sources of staggering energy, brighter than entire galaxies. They were called quasars, quasar-stellar radio sources. In the 1960s, quasars confounded astronomers. They looked like stars, but their light came from billions of light-years away. For something so distant to appear so bright, its true power had to be unimaginable. No ordinary star could account for it. The only explanation that fit was that matter was falling into a compact, invisible monster, releasing energy as it spiraled inward. Around the same time, X-ray astronomy was born. Satellites launched above Earth's atmosphere revealed strange sources of high-energy radiation. One, known as Cygnus X1, shone not from a star, but from something hidden. Careful study of its companion star's orbit revealed the truth. The visible star was circling an unseen object, massive yet dark. Its mass exceeded any known neutron star. It was, almost certainly, a black hole. The storm had stepped out of mathematics and into reality. Naming the unnamable, the term black hole was not coined until 1967, when physicist John Wheeler used it in a lecture. Before then, they were described with clumsy phrases: frozen stars, collapsed objects, gravitationally completely collapsed stars. But Wheeler's phrase captured their essence: regions where space itself had caved in, leaving a hole in the fabric of the cosmos. The name stuck, and with it, the storm gained identity. Black holes were no longer whispers in equations or curiosities in speculation. They were real entities, detectable, measurable, swallowing light itself. From curiosity to commonplace, what began as an oddity grew into a revelation. Black holes were not rare. They were not confined to exotic corners of the universe. They were common by the late 20th century. Evidence mounted that supermassive black holes lurked at the centers of galaxies. Stars near the heart of the Milky Way moved in tight, rapid orbits, as though circling an invisible anchor. Radio emissions traced to the region known as Sagittarius A*, suggested a central engine for million times the mass of the Sun. In distant galaxies, jets of plasma stretched thousands of light-years, ejected at near-light speeds. Only black holes, devouring matter with ferocity, could power such storms. Quasars, once mysterious, became understood as galactic cores ablaze with accretion. The storm was not an exception. It was a rule, the turning point, the discovery of Cygnus X1, the recognition of quasars, and the growing evidence for supermassive black holes marked a turning point. Humanity now knew that the universe was littered with these storms. Some were stellar remnants, born when massive stars collapsed. Others were giants, millions to billions of times the Sun's mass, shaping the very galaxies around them. What Mitchell and Laplace had imagined as dark stars had become flesh. What Einstein had doubted had become inevitable. What had glimpsed in mathematics was written across the sky in radiation and orbits and silence. The storm that ate the sky was real, and it was everywhere. The question of origins, but discovery raised new questions. How did these storms form? How could something so compact, so absolute, arise from ordinary stars or galaxies? Stellar black holes seemed comprehensible, the collapse of massive stars at the end of their lives. But supermassive black holes, billions of solar masses, appeared too early, too suddenly, in the universe's history. Quasars blazed less than 1 billion years after the Big Bang. How could such titanic storms have formed so quickly? The discovery phase did not end with confirmation. It ended with unease. Every answer only sharpened the mystery. The revelation that black holes were real did more than surprise. It unsettled the very foundations of science. For here was a phenomenon that did not merely bend the rules of physics, seemed to erase them. The collapse of space-time ordinary. Stars obey predictable laws. They shine by nuclear fusion, resist gravity by pressure, and eventually fade into white dwarfs or neutron stars. Their stories follow patterns, their ends are comprehensible. But black holes broke that rhythm when a massive star collapses under its own gravity. There is no force known to resist the implosion. Not even the degeneracy pressure that supports neutron stars can withstand it. The collapse continues, crushing matter into a density so extreme that the very equations of physics begin to falter. At the heart of this storm lies the singularity, a point where space-time itself is infinitely curved, where all known laws dissolve into paradox. General relativity predicts it, yet cannot describe it. Quantum mechanics denies such infinities, yet cannot replace them. The shock was not just in the mathematics, but in the implication. Nature itself allows places where the known rules of reality cease to function. Black holes were not just objects, they were boundaries to human knowledge. The event horizon, edge of reality, even stranger, was the horizon. The event horizon is not a surface like a planet's crust or a star's atmosphere. It is a boundary in space-time itself. Cross it, and return becomes impossible. Not just for matter, not just for signals, but for light itself, the very speed limit of the universe. This was staggering. For centuries, light had been considered the ultimate constant, the unreachable velocity. Einstein's relativity enshrined it as the barrier of causality, the absolute frame upon which physics rests. Yet here, in these storms, light itself was caged. The event horizon was the most radical concept imaginable, a cosmic one-way door, beyond which the sky itself is eaten. For scientists, the philosophical weight was immense. The universe had boundaries where causality broke, where no observer outside could ever know what lay within. To accept black holes was to accept permanent ignorance, regions of the universe cut off forever, hidden behind the veil of the horizon. Einstein's doubt and Hawking's revelation, Einstein himself resisted, though his equations predicted collapse. He dismissed physical black holes as improbable. Nature, he believed, would not permit such monsters. He imagined that some undiscovered mechanism would halt the collapse before the horizon formed, but the universe disagreed. By the mid-20th century, evidence grew overwhelming. Quasars blazed brighter than galaxies, powered by invisible engines. X-ray binaries revealed companions too massive and compact to be anything else. Black holes could no longer be denied. Then came the voice of Stephen Hawking. who in the 1970s transformed black holes from terrifying curiosities into essential laboratories of physics. Hawking showed that black holes are not entirely silent. Through quantum effects at the horizon, they should emit faint radiation, now known as Hawking radiation. If true, then black holes are not eternal. They can evaporate. They can die. This revelation was staggering. The most perfect prisons in the universe might still whisper and ultimately dissolve. Black holes were not only destroyers, they were paradoxes, both devourers of information and possible emitters of it, power beyond comprehension. The shock deepened when astronomers calculated the power unleashed by black holes. As matter falls inward, it heats, compresses, and accelerates. Accretion disks around black holes glow hotter than the cores of stars. Jets erupt, spearing through galaxies, stretching for millions of light years. The energy efficiency of accretion is extraordinary. Pound for pound, falling into a black hole releases far more energy than nuclear fusion. In fact, it is the most efficient engine in the universe. Quasars, driven by supermassive black holes, outshine entire galaxies of stars. What startled scientists most was scale. These storms are not small. Supermassive black holes sit at the centers of nearly every galaxy, including our own. Their influence is not confined to swallowing stars. They shape galactic evolution itself, regulating star formation, carving cosmic structures, and perhaps even steering the growth of the universe. Black holes are not rare curiosities. They are the rule. The universe is not dotted with occasional storms, it is built around them. The information paradox. But the greatest shock of all was the information paradox. According to quantum mechanics, information cannot be destroyed. The state of particles must always be, in principle, recoverable. But black holes seemed to erase information permanently, swallowing it beyond the horizon. If black holes truly destroy information, then quantum theory is wrong. If they do not, then relativity fails. Here lies one of the deepest paradoxes in physics, two pillars of science, both verified to extraordinary precision, give contradictory answers when faced with the storm that eats the sky. This paradox was not merely technical, it was existential. If the laws of physics break within black holes, then the dream of a complete theory of nature is unfinished. The storms do not only devour stars, they devour certainty, the terror of universality. The most disturbing realization was universality. Black holes are not exotic accidents. They form whenever enough mass collapses. Stars above a certain threshold end as black holes. Galaxies harbor them at their cores. Collisions create them anew. There is no law that forbids their growth. A black hole can swallow, merge, and expand without limit. In principle, a black hole could consume entire galaxies. Even the universe itself might collapse into a final storm. A cosmic singularity where all of space-time ends. This possibility moved black holes from curiosities to existential threats, not to humanity specifically, but to the idea of permanence itself. A shattered intuition, the scientific shock was complete. The universe was not eternal light and graceful stars. It was also storms of silence, holes in space-time, edges of knowledge. The rules that seemed unbreakable were broken. The sky itself could be eaten. This was not just a discovery. It was a revelation of fragility. If even light, the swiftest thing in the universe, could be captured, then what truly endures? If space-time itself could collapse, then what does it mean for reality to be stable? The shock of black holes was not only in their power, but in their meaning. They were proof that the universe is stranger than imagination, darker than myth, and more fragile than belief. Discovery and shock were only the beginning. Once the existence of black holes could no longer be denied, the pursuit shifted. What were these storms, truly? How did they form? How did they grow? And what secrets lay hidden within their silence? The age of speculation gave way to the age of investigation, an era defined by instruments stretching human senses into realms where light falters, where gravity reigns supreme. Listening to X-rays, seeing the unseen black holes themselves are invisible, no light escapes their horizons. Yet their presence can be traced by the havoc they unleash on their surroundings. Matter spiraling inward does not vanish quietly, it blazes. As gas falls, it collides, compresses, and heats to millions of degrees. It radiates in X-rays, flickering, like cosmic lightning before being swallowed. X-ray observatories, launched above Earth's atmosphere, became the first stethoscopes to listen to this violence. NASA's Chandra X-ray Observatory, ESAS, XM, Newton, and others captured the high-energy signatures of matter on the brink of oblivion. In these X-ray flickers, astronomers mapped accretion disks, swirls of gas orbiting perilously close to event horizons at speeds approaching light. These signals revealed astonishing details. Gas could orbit a black hole dozens of times in a second, tracing the very curvature of space-time. Flickering patterns hinted at turbulence, magnetic fields, and shocks too extreme for earthly laboratories. The storms were not quiet voids. They were cauldrons of energy, chaotic and violent, yet governed by laws that still obeyed Einstein's equations up to the brink of collapse. The giants at the galactic heart in time. Evidence mounted that not all black holes were remnants of stars. Some were giants millions or billions of solar masses, lurking at the centers of galaxies. The Milky Way itself carried proof. Astronomers studied the orbits of stars near the radio source known as Sagittarius A*. Over years, precise measurements revealed stars whipping around an invisible anchor at thousands of kilometers per second. Only a supermassive black hole, for a million times the sun's mass, could explain their dance. Other galaxies revealed even greater titans. In the core of M87, a black hole over 6 billion solar masses dominated its surroundings. Jets of plasma streamed from its poles, stretching across tens of thousands of light years. These jets, launched at near-light speeds, carried energy rivaling entire galaxies. The storm not only consumed but reshaped its cosmic environment, regulating star formation, sculpting matter across scales larger than imagination. The investigation revealed a profound truth. Galaxies and black holes are inseparable. Every major galaxy hosts a supermassive black hole at its center. Their growth and the galaxy's evolution are entwined, perhaps even determined by one another. The storm is not incidental. It is structural. The tremors of space-time in 2015, a new window opened. The Laser Interferometer Gravitational Wave Observatory LIGO announced the first detection of gravitational waves, ripples, in space-time itself. Two black holes, spiraling together in their final death dance, collided. The merger released more energy in gravitational waves than all the stars in the observable universe emit in light during the same instant. For the first time, humanity did not just see or infer a black hole. It heard one. The chirp of the collision, lasting less than a second, was the sound of the storm itself, a whisper from the fabric of reality. Since then, dozens of such detections have followed, with Virgo in Europe and Kagra in Japan joining the search. Each event tells a story of stellar remnants colliding, of masses once hidden revealed through their final embrace. Black holes do not live in isolation. They merge, they grow, they create greater storms. The universe is alive with their tremors. The first glimpse of the shadow for decades. Scientists dreamed of seeing the unseeable. Though a black hole emits no light, the swirling matter around it creates a silhouette, a dark shadow against a glowing backdrop. Achieving such an image required a telescope the size of Earth, and so, scientists built one, not as a single instrument, but as a network of radio dishes spread across the planet, synchronized into one global eye. In 2019, the Event Horizon Telescope EHT unveiled the first image of a black hole's shadow, the one at the center of galaxy M87, a glowing ring of plasma encircled a void of darkness. The shadow matched predictions of general relativity almost perfectly. For the first time, humanity saw the storm that eats the sky, its edge traced in fire and silence. In 2022, the EHT revealed the shadow of Sagittarius A*, the supermassive black hole at the heart of our own galaxy. A cosmic mirror, a reminder that the storm is not only distant, but here just 26,000 light-years away, shaping the galaxy that is our home. The puzzle of information as data poured in, deeper puzzles emerged. Chief among them was the question of information. When matter falls into a black hole, does its information, the quantum details of its state, vanish forever? Relativity suggests yes, the event horizon hides all within. But quantum mechanics insists no, information cannot be destroyed. The conflict between these pillars of physics became a crisis. Hawking's discovery of radiation offered a tantalizing clue. If black holes emit faint thermal radiation, then perhaps they can also release information, though in ways not yet understood. Some theorists propose the holographic principle, that all information swallowed is stored on the horizon itself, encoded like data on a cosmic screen. Others suggest that wormholes or quantum entanglement weave the lost information back into the universe. The investigation had reached the frontiers of physics. Black holes became not just astronomical objects, but laboratories for the ultimate laws of reality, anomalies and whispers. Even as theories grew, anomalies persisted. Some galaxies showed black holes far larger, far earlier than current models. Aloud, quasars in the early universe blazed when galaxies should have been too young to host such giants. How had they grown so quickly? Did they form from colossal primordial seeds, born in the first moments after the Big Bang? Other whispers emerged from simulations and observations. Could black holes bounce? Could they leave behind remnants, bridges, or echoes in space-time? Some gravitational wave data even hints at post-merger vibrations that might betray physics beyond relativity. Each anomaly was not an answer, but a deepening of the storm within the storm. Step by step, the investigation revealed not simplicity, but complexity. Black holes were not silent voids. They were dynamic, roaring storms that consumed, created, regulated, and perhaps even recycled. They were paradoxes, destroyers and creators, prisons and engines, finalities and beginnings. Every new observation was both revelation and riddle. The X-ray flickers, the gravitational waves, the glowing rings of the Event Horizon telescope all confirmed black holes exist, yet all raised deeper mysteries about their nature. In chasing the storm, Humanity learned that to investigate is not to resolve, but to widen the horizon of the unknown. The investigation had revealed that black holes were real, common, and powerful. Yet the closer science drew to their shadows, the darker the questions became. For each answer raised another paradox, another threat to the coherence of physics. The storm that ate the sky was no longer simply a region of collapsed space-time. It was a riddle woven into the fabric of reality. The paradox of information. At the heart of the storm lies a conflict between two pillars of science: general relativity and quantum mechanics. Relativity describes black holes with elegance, space-time curves, horizons form, matter collapses. Information that crosses the horizon is lost forever. To an external observer, the storm erases history itself, but quantum mechanics declares such destruction impossible. The principle of unitarity insists that information cannot be obliterated. Every quantum state must, in some form, endure. If black holes annihilate information, then the foundations of quantum theory crack. If they preserve it, then relativity falters. The paradox remains unresolved, a storm within the storm. Some propose that the horizon is not smooth, but a seething firewall of quantum energy that burns information away at the edge. Others suggest that information clings to the horizon as a hologram, written into the geometry of space-time itself. Still others envision entangled wormholes that ferry data into hidden realms. The paradox escalates not only science, but philosophy. If the universe can erase its own history, what does causality mean? If reality can lose its memory, what is the meaning of time? Hawking's evaporation in 1974, Stephen Hawking deepened the mystery by merging relativity with quantum field theory. He showed that black holes should radiate faint energy now called Hawking radiation. This discovery transformed black holes from eternal prisons into temporary storms. They may not last forever. Over unimaginable timescales, they evaporate, releasing their mass as radiation until nothing remains. But Hawking's insight sharpened the paradox. If black holes evaporate, where does the information they contained go? Does it vanish with the horizon? Or is it somehow encoded in the outgoing radiation, scrambled yet preserved? The implications ripple outward. If Hawking radiation carries information, then black holes are not absolute erasers. If it does not, then quantum mechanics collapses. Either way, the storm forces physics to its breaking point. Gateways and bridges speculation deepens further when considering what lies at the storm's center. Relativity predicts a singularity, a point where density is infinite and space-time ends. But infinities are signs of incompleteness, not truths. Many physicists suspect that singularities hide new laws waiting to be discovered. Could black holes be gateways rather than graves? Some theories suggest that collapsing matter tunnels into other regions of space-time, perhaps birthing entire new universes. In this view, every black hole is a cosmic womb, its storm destroying one world while seeding another. Others envision black holes as bridges, wormholes, threading distant parts of the cosmos. If true, then black holes are not merely storms that eat the sky. They are doors, locked, but waiting for the right key. These ideas remain speculative, yet they capture the imagination, for they hint that destruction and creation may be two faces of the same storm. The cosmic scale of the storm, what once seemed like exotic objects, proved to be central actors in cosmic evolution. Black holes do not simply consume, they regulate. Their jets heat interstellar gas, preventing premature star formation. Their feedback shapes galaxies, balancing creation and collapse. The storm is thus not peripheral, it is structural. Without black holes, galaxies might collapse into chaotic bursts of stars, exhausting their fuel too quickly. With them, galaxies are sculpted, paced, and sustained. The paradox grows. The same storms that devour also sustain. Black holes are both predators and gardeners of the cosmos. They shape the very sky they threaten to eat. The mystery of singularities that the storm's core lies the singularity, a point where the equations of relativity predict infinite curvature. Here, time and space lose meaning. Yet no theory of physics can describe this region. Quantum gravity, the unification of the very large and the very small remains elusive. What happens at the singularity? Is it truly a point of infinite density, or a phase of matter and space-time we do not yet understand? Could it be a bounce, a transition, a bridge? The singularity is more than a puzzle. It is a wall. Every theory of physics must confront it, and every attempt so far falters. The storm devours not only light, but knowledge. The ultimate terrorers, science, traced the storms. An even greater terror emerged. Black holes are not confined to stars or galaxies. They can grow without limit. They can merge, accrete, and expand. There is no law that caps their size. Some speculate, could the universe itself end in collapse? If cosmic expansion were ever to reverse, if dark energy's influence waned, then the universe could implode into a final singularity, a black hole. Of all things, a storm that devours not the sky, but the cosmos itself. Even if expansion continues forever, the end is still bleak. Over trillions of years, stars will fade, galaxies will die, and black holes will dominate. In the far future, when the last star has burned, only black holes will remain the final storms, slow and silent, evaporating into darkness. The ultimate fate of the cosmos may be nothing but the echo of their death, a deepening mystery each. Escalation widens the gap between what is known and what is hidden. Information paradoxes, pit relativity against quantum mechanics. Hawking radiation suggests storms are not eternal, yet offers no clear resolution. Wormholes and universes within universes remain tantalizing but unproven. Singularities stand as silent walls where knowledge ends. The storm that eats the sky is no longer only an astrophysical object. It is a boundary of human thought, a mirror showing the limits of understanding. The deeper we look, the darker it grows. The deeper the mystery grew, the more urgently physicists sought explanations. Black holes had become not merely astronomical curiosities, but laboratories of ultimate truth. Within their horizons, relativity and quantum mechanics collided, revealing contradictions that could not be ignored. To explain these storms was to glimpse the next great chapter of physics. Relativity and the singularity theorems. In the 1960s, mathematician Roger Penrose proved the first rigorous theorems of collapse. Under general relativity, once a star surpasses a critical threshold, collapse into a singularity is inevitable. Einstein's equations allowed no escape. Stephen Hawking extended these results, showing that singularities were not rare exceptions, but unavoidable features of space-time. This was a profound shock. It meant singularities were not artifacts of symmetry or simplification. They were real, written into the equations. Black holes were not accidents. they were destinies. But this also highlighted the problem. Singularities are places where relativity breaks down. The theory that predicted them could not describe them. The mathematics dissolved into infinities. To confront the storm, a deeper theory was needed. Quantum mechanics and the information puzzle here. Quantum mechanics raised its hand. The quantum world is not infinite but discrete. Energy comes in quanta. Information is never destroyed. Yet black holes seemed to annihilate it. This led to the black hole information paradox, one of the greatest crises in modern physics. If information vanishes into singularities, then quantum mechanics is incomplete. If it does not, then relativity fails. Proposals multiplied. Some argued for the holographic principle developed by Gerard T. Hooft and Leonard Susskind. According to this idea, all the information of a volume of space can be encoded on its boundary. Applied to black holes, this means the information is not lost but inscribed upon the horizon itself, like data on a cosmic screen. Others proposed black hole complementarity, the notion that information both falls in and remains outside, depending on perspective. Reality itself might be observer-dependent, stitched together from paradox, but none of these theories resolved the puzzle fully. Each was a step, not a destination. The firewall paradox in 2012. A new shock emerged. The firewall paradox. If black holes preserve information, then the horizon may not be smooth, as relativity predicts. Instead, it could be a wall of searing quantum energy. Any particle or astronaut crossing it would be incinerated instantly. This idea violated Einstein's principle of equivalence, which insists that crossing the horizon should feel uneventful. The smooth fabric of space-time would be replaced by a violent barrier. The firewall deepened the paradox. If true, it rewrote relativity at the edge of black holes. If false, then information loss returned. Either way, the storm resisted reconciliation. Cosmic censorship and other speculation concerns whether singularities must always hide behind horizons. The cosmic censorship hypothesis, proposed by Penrose, suggests that nature conceals singularities from the universe, cloaked behind horizons so their chaos never leaks into the observable cosmos. But is censorship absolute? Could there be naked singularity storms without horizons, where infinities are laid bare? If such objects exist, they would shatter determinism, unraveling cause and effect. Some exotic solutions to relativity allow them, yet so far none have been observed. The question remains, does nature keep its secrets, or does it sometimes expose the raw storm beneath? White holes and time's reversals speculation also turns to the idea of white holes, the theoretical opposites of black holes. If a black hole devours everything, a white hole expels everything. Nothing can enter. Everything only escapes. Relativity allows their existence, but no evidence supports them. Some physicists propose they may exist in the quantum foam of space-time, flickering in and out of existence. Others suggest black holes at their death might transform into white holes, releasing what they consumed. If true, then storms may not be final. They may be transitions, phases in a cycle of collapse and eruption, destruction and release, universes within universes. Another daring speculation sees black holes as cosmic wombs. When a star collapses into a singularity, it may not end in destruction, but trigger a new universe. The singularity could be the seed of a separate cosmos, budding off from our own with its own spacetime and laws. If this is true, then our universe itself may have been born from the heart of another black hole. The storm that eats the sky may also plant new skies elsewhere. This idea, while unproven, reframes black holes not as ends but as beginnings. Every collapse may be creation unseen, dark energy and the accelerating storm, the discovery of dark energy. The force driving cosmic acceleration raise new questions. Could black holes be linked to it? Some theories suggest that vacuum energy, the same force accelerating galaxies apart, may also drive the growth of black holes. Others speculate that black holes could even be reservoirs of dark energy, influencing cosmic expansion. If so, the storms may not only shape galaxies, they may be entangled with the fate of the universe itself, toward quantum gravity. These speculations point to one need, a theory of quantum gravity, neither relativity nor quantum mechanics alone can describe black holes fully. A unifying framework is required, one that merges the continuous fabric of spacetime with the discrete quanta of the micro-world. Candidates exist: theory, loop quantum gravity, emergent spacetime from entanglement. Each offers glimpses of resolution, strings vibrating at Planck scales, loops of geometry weaving spacetime, quantum entanglement building the fabric of reality, but none are complete. None yet reconcile all paradoxes. The storm remains unmastery. The meaning beneath the model's theories and speculations multiply, each stretching imagination. They show black holes are not only astrophysical objects, but conceptual frontiers. They reveal that destruction and creation, information and oblivion, relativity and quantum theory are entangled. The storm that eats the sky is not only a question of astronomy, it is a mirror for physics itself, showing its fractures, its limits, its possibilities. The speculation may remain unresolved, but it points to a deeper truth. To understand black holes is to approach the foundations of reality. To chase a storm that swallows light is to fight against the limits of perception. Black holes, by their nature, reveal nothing of themselves. Their horizons are absolute silence. Yet science, restless and unyielding, has built instruments to see the unseen, to hear the inaudible, to map the shadows cast by absence itself. In the pursuit of black holes, humanity has turned the earth into a sensor, the heavens into a laboratory, and light into a messenger. Listening to the universe, gravitational wave observatories in 2015. The world heard the storm for the first time. The Laser Interferometer Gravitational Wave Observatory LIGO registered a faint ripple in spacetime. The merger of two black holes, over 1 billion light-years away. The signal lasted less than a second, a rising chirp. Yet in that whisper, more power was released than in all the stars of the observable universe combined. Since then, LIGO, along with Virgo in Europe and Kagra in Japan, has catalogued dozens of mergers. Each detection is more than an event. It is a story written in gravitational waves. Some reveal black holes heavier than theory expected. Others suggest populations that defy models of stellar evolution. Each chirp widens the catalogue, sharpening the picture of how storms are born, how they grow, and how they die. Gravitational wave astronomy is young, but it is transformative. It does not look at the universe, it listens. It hears the tremors of space-time itself. Vibrations of reality produced by storms and collision. The Event Horizon Telescope, a planet-sized eye while gravitational waves reveal black holes in motion. light still offers their most haunting portraits. The event horizon. Telescope EHT, a network of radio dishes scattered across Earth, acts as one vast interferometer the size of the planet. Its resolution is sharp enough to see the silhouette of a black hole against the glow of matter swirling at its edge. In 2019, the EHT unveiled the first direct image of a black hole, the shadow of the 6 billion solar mass giant in the galaxy. M87, a ring of fire encircled a void, the absence of light itself. 3 years later, it captured the shadow of Sagittarius A*, the supermassive black hole at the center of our own Milky Way. These images confirmed Einstein's predictions to extraordinary precision. The size and shape of the shadows matched general relativity almost perfectly. Yet they also hinted at turbulence and complexity in the plasma around the horizon, clues about magnetic fields, accretion flows, and perhaps even tests of quantum effects near the edge of the storm. The EHT continues to refine its vision. Future expansions will sharpen the images, producing movies of black holes in action, allowing humanity to watch storms evolve in real time. The James Webb Space Telescope, peering into the dawn. The James Webb Space Telescope JWST extends human sight deep into infrared, allowing astronomers to probe the earliest galaxies. In its first year of observations, Webb discovered quasars blazing when the universe was less than 1 billion years old. Some already harbored black holes of unimaginable size, hundreds of millions of solar masses, far too large for conventional growth models. These discoveries challenge theories of how black holes form. Did they begin as remnants of the very first stars, swelling by accretion? Or did they form from colossal direct collapses of primordial gas clouds, bypassing stellar origins entirely? Webb's gaze offers tantalizing data, but the mystery deepens. Storms seem to have risen earlier and faster than expected, shaping the young universe in ways not yet understood. Chandra, XM Newton, and the high-energy sky, while Webb looks to the distant past. X-ray observatories like Chandra and XM Newton probe the high-energy present. They map the blazing disks of matter spiraling into black holes, where friction, magnetism, and turbulence heat gas to millions of degrees. Chandra has revealed jets erupting from galactic centers, piercing through interstellar gas, heating clusters, regulating star formation. These observations prove that black holes are not passive consumers. They are architects of galaxies, engines that shape their environments. Even more, X-ray data has uncovered quasi-periodic oscillations, regular flickers in the glow of accretion disks. These may be signatures of matter orbiting at the very innermost stable paths, tracing the contours of curved space-time just above the horizon. In those oscillations, physicists glimpse the fingerprints of relativity itself. Future missions, expanding the arsenal. The future of black hole science lies in instruments yet to fly. The Laser Interferometer Space Antenna LISA, scheduled for the 2030s, will float in solar orbit, listening for gravitational waves from supermassive black hole mergers events to vast foreground-based detectors to hear. Athena, a planned European X-ray observatory, will map hot gas in exquisite detail, tracing the influence of black holes across clusters and galaxies. The Square Kilometer Array, SKA, the largest radio telescope ever built, will detect pulsars orbiting black holes, using them as cosmic clocks to test relativity in extreme conditions. Together, these instruments will not only observe storms, They will dissect them. They will map their growth, their feedback, their whispers of quantum mechanics, simulations, building virtual universes beyond observation. Science turns to simulation. Supercomputers model galaxies seeded with black holes, tracing their growth across billions of years. Programs like Illustrious and Eagle recreate cosmic webs where feedback from black holes regulates star formation, producing galaxies that resemble those we see. Other simulations dive inward, modeling accretion flows, magnetic turbulence, and jet formation. Some explore quantum gravity candidates, testing whether loop quantum cosmology or string theory can resolve singularities. Simulations do not replace observation, but they provide a laboratory of possibility. They allow science to test scenarios the universe has not yet revealed, to compare models with the data from telescopes and detectors. In the union of observation and simulation, the storm becomes clearer, though never fully transparent. The frontier of testing each instrument probes a different wavelength, a different messenger. Gravitational waves reveal mergers and collisions. Radio, telescopes, map jets, and shadows. Infrared observatories peer into the cosmic dawn. X-ray. Satellites trace the heat of accretion. Together, they form a symphony of inquiry, a multi-messenger astronomy that listens to the storm from every angle. The frontier lies at the intersection of these messengers. When gravitational waves from a merger coincide with X-ray flares or radio jets, the picture sharpens. When simulations match observations across all spectra, the theories gain strength. Yet even here, mysteries remain. Why do some black holes spin near the speed of light, while others drift more slowly? Why do some jets stretch for millions of light years, while others remain weak? Why do supermassive black holes appear fully formed so early in cosmic history? The tools sharpen, but the storm resists full comprehension. A human reflection, these instruments are not mere machines. They are extensions of the human will to know. They represent deserts filled with radio dishes, mountains crowned with mirrors, satellites orbiting in silence, lasers stretching kilometers across the earth. They are collaborations of thousands of minds, generations of labor, billions of hours dedicated to chasing what cannot be seen. There is something profoundly moving in this pursuit. Black holes are the most destructive forces known, and yet humanity has chosen not to fear but to study them. We build eyes to watch the storm, ears to hear its rumble, minds to model its hidden truths. The storm that eats the sky is a challenge, not only to physics but to imagination. And in rising to meet it, humanity discovers not only the nature of black holes, but the depth of its own curiosity. The journey into the storm ends where it began, in silence. A silence not of emptiness, but of awe. For black holes are not only scientific puzzles, they are mirrors held up to the universe and to ourselves. They ask questions as old as thought. What endures? What fades? What lies beyond the edge of knowledge? Mortality writ large. To contemplate a black hole is to confront mortality. Stars die, galaxies collapse. Even light, the swiftest thing in existence, cannot endure. The event horizon is not just an astronomical boundary. It is a cosmic metaphor, a reminder that all things have limits. Human lives are short. Yet black holes remind us that even the greatest structures in the cosmos share the same fate. They live, they grow, they die, over unimaginable spans of time. Even the storms themselves will evaporate through Hawking radiation, leaving behind only faint whispers of energy. In the far future, when galaxies are dark and stars long extinguished, black holes will be the last monuments of matter. And when they too fade, the universe will pass into silence. The storm that eats the sky is thus not only destruction, it is prophecy, creation through collapsing. Yet within this destruction, there is creation. Black holes are not sterile voids. They power quasars, the brightest beacons in the universe. Their jets sculpt galaxies, regulating star formation, shaping the very conditions for life. Their collisions forge gravitational waves, ripples that now serve as messengers of cosmic truth. Perhaps more profoundly, black holes may even seed new realities. Some theories suggest that each singularity births another universe, hidden from ours. If so, then collapse is not final but generative. The death of one sky may ignite the birth of another. In this sense, black holes embody the paradox of existence itself. Endings that are also beginnings, destruction that is also creation. They are storms, yes but storms, that sow as well as reap the fragility of laws. Black holes expose the fragility of the very laws we depend upon. Relativity and quantum mechanics, each so successful in their domains, fracture when confronted with the singularity. Information, causality, even time itself become uncertain. What does it mean to live in a universe where the deepest truths are incomplete, where the very fabric of reality contains contradictions? Perhaps it means that certainty is an illusion, that knowledge is always provisional. Perhaps it means that mystery is not the exception, but the essence. The storm does not only devour matter, it devours human arrogance. It forces humility, reminding us that even our proudest theories are shadows cast on a greater truth, humanity and the storm. And yet, fragile as we are, humanity gazes into these storms and dares to understand. On a small planet orbiting an ordinary star, a species with finite lives has built machines to see horizons billions of light years away. With radio dishes, satellites, and detectors, we have traced the very edges of invisibility. There is something defiant in this. Black holes erase information, but humans insist on learning. They devour light, but humans build eyes large enough to glimpse the shadow. They rumble in gravitational waves, and humans stretch lasers across continents to hear their whispers. The paradox of black holes is also the paradox of humanity. Fragile beings staring into infinite darkness, refusing silence, insisting on meaning, impermanence, and beauty. If black holes teach anything, it is impermanence. Nothing lasts. Not stars, not galaxies, not even space-time itself. And yet, this impermanence does not negate beauty, intensifies it. Nebulae glow with newborn stars. Galaxies spiral in luminous arms. Even the shadows of black holes blaze with plasma. All of it is transient, and precisely because it is fleeting, it is precious. To live in a universe with black holes is to live in a universe where nothing is safe from change. But it is also to live in a universe where every moment of light, every spark of life, is more miraculous for its fragility. The end of the sky, what, then, of the future? Physics offers scenarios. If dark energy continues to accelerate the cosmos, galaxies will drift apart until even their light cannot reach one another. Stars will burn out. Black holes will dominate, then evaporate. The universe will end in heat, death, silent and cold. Or perhaps the storm will be larger still. Perhaps the universe will one day collapse into a singularity of its own, a final black hole. a storm that does not eat the sky but the cosmos entire. Either way, the message is the same. Permanence is an illusion. The universe itself is mortal. The storm is not anomaly but destiny, a teacher in the dark, and yet, for all their terror, black holes are teachers. They reveal the edges of knowledge. They show where theories fail and where new ones must be born. They remind us that mystery is not weakness but opportunity. Perhaps that is their greatest gift, not the light they consume, not the matter they swallow, but the questions they leave behind. Questions that drive human curiosity forward. Questions that will outlast the lives of stars. In their silence, black holes speak. In their darkness, they illuminate. Closing vision. Imagine the universe, billions of years from now. Galaxies faded, stars gone, only black holes remain silent, storms drifting in a sea of darkness. One by one they evaporate, their whispers fading. Into nothing, the sky empties, the cosmos ends. And yet, here and now, before that silence, humanity exists. Fragile, fleeting, yet capable of wonder. Capable of building instruments that trace shadows on the edge of eternity. Capable of telling stories of storms that eat the sky. Perhaps that is enough, to know, to see, to bear witness, to find meaning, not in permanence, but in the fleeting fire before the dark. The storm that eats the sky is real. It is terrifying. It is inevitable. But it is also beautiful because it reminds us that even in a universe of endings, the act of seeking, of questioning, of wondering, is itself a kind of light dot. And so the storm is not only destruction, it is revelation. It shows us the boundaries of reality and whispers that beyond collapse may lie truths more profound than imagination itself.